What's going on, guys? Hopefully you've had a good spring break and hopefully you're ready to get back at it. We are going to pick up where we left off. First lecture, returning from spring break, and first lecture, returning from spring break by distance learning. You guys know the deal. New York City not doing so well, but hopefully you've all been well, you've all been safe. Hopefully your lives haven't been disrupted too badly in terms of employment or any other things it's kind of bad for everybody, but hopefully you guys are doing okay enough to focus on your school, because we're going to keep learning. We are going to continue with series. Last time, just to jump right into it, because I didn't really have any questions from the lecture that I did last time. So this is actually, I already have chalk all over me because this is actually the second lecture I'm doing today. Last time we spoke about estimating series. So we saw the fact that when a series adds up to something, oh God, I don't even know where to actually start now. It's actually feels like it's been forever. How far back should I go? I don't know. Well, a series, let's start from the beginning, just like a quick 30-second overview. A series is the sum of the terms of a sequence. We really care about infinite series, not the finite ones, because those are not interesting. But every now and then, you can add up an infinite number of things, and it adds up to something mathematically meaningful, like a real number. And last time we did a lot of tests, about 10 of them, that actually tell us when an infinite sum actually adds up to something meaningful. These were called the series convergence test, talking about things like test for divergence, which tells you when a series diverges, the ratio test, the telescoping series test, the root test, the p-series test, the comparison test, the limit comparison test, the integral test, all this good stuff, the geometric series test. There are all these tests that told us when a series converges, two of which actually told us what it converges to, the geometric series test and the telescoping series test. So, in general though, what a series converges to is pretty difficult to determine in general, at least at the Calc 2 level. If you go to higher math classes, you will actually learn about different theorems and methods of determining what a series converges to. But so far, we are at a huge disadvantage. So what we looked at the last time we were here was how can you estimate a series? Like if we were to add up the nth partial sum, like how close is that to the actual answer? And we looked at that in the cases of the alternating series test, we looked at that in the case of the integral test and the comparison test, and we just kind of saw how good an approximation was the nth partial sum to the actual sum of the series. So now we're going to continue our series lecture, and we'll actually stick with series for 2 or 3 more lectures, and then we'll actually move on to some other stuff. But right now we're going to move on to something very cool, which is called power series. So this is the next topic that we're going to cover. Let's just jump right into it because we only have 50 minutes to get through this. The next section is section 11.8, which now reminds me, I don't think I had posted homework. Note to self, post homework for sections up to 11.8 at this point. Maybe even 11.9, depends on how far I get to today. We're going to talk about power series. Very, very important. Now, series are important in general, as I've been telling you guys. It's just an important thing all around, and I'm not just talking about calculus. In like math in general, series is a big deal. Power series is particularly a big deal in calculus. It's one of the main reasons why we study series in calculus, because power series are actually going to help us get a lot done by way of calculus-specific computations. It is important outside of calculus class, but as far as calculus is concerned, this is one of the main applications of series, why we even care about infinite series in the first place, because of power series and what they can help us actually do. So let's actually just jump into it. What is a power series? So I wrote out the definition here. Let me move this out of the way. So a power series centered at x naught, this is something that is just making it more specific where your series is centered at. I'll talk about that in a little bit. What does it mean to be centered at x naught? Is a series of this form. That's it. So you have the series from n equals 0 to infinity of c sub n x minus x naught to the nth power. Now, this isn't really a part of the definition. I just wrote out a few terms here for you to see what this would actually look like. This would look like c0 plus c1 x minus x naught plus c2 x minus x naught squared, etc. It will actually look like that if you write it out. Now, this object should look somewhat familiar to you. Now, if it doesn't actually look familiar to you, what I did was I plug in x naught equals 0 specifically. That will make our power series look like this. That will start to look like this. So I have c naught plus c1x plus c2x squared plus c3x cubed, c4x4, so on. Now, you might start to think, hopefully you start to think this, hey, Jhevon, that kind of starts looking like a polynomial. And yes, that's exactly it. A power series is kind of a way to write down an infinite polynomial of infinite degree. Now, that should obviously kind of have, your intuition should be telling you that that should have some value, because polynomials are really nice when it comes to like math in general, but also calculus. They're continuous everywhere. You can differentiate them easily. You can integrate them easily. You both use the power rule for derivatives and integrals to differentiate and integrate them. It's very nice to do calculus with a polynomial. So here, we're talking about an infinite polynomial. Whoa. So it turns out that these guys have a lot of uses, but we are going to talk about how does it actually make sense? What does it actually mean to be this infinite polynomial? What does this series actually mean, really? So I wrote this out just to be suggestive of the fact that this is kind of talking about a polynomial of infinite degree, but this is just a power series centered at 0 specifically. Now, where does the name power series come from? A function that looks like y equals x to the n, so like y equals x squared, y equals x to the half, y equals whatever. Functions of that form, they're called power functions. So if you just have a series where each term is a power function, basically what you get is a power series. That's where the name comes from, right? So it's just a series of power functions you call a power series. And one way you can think of this, one way that we're going to like to think of it, we're actually not going to use that a lot, but it's actually a pretty good way to think about it, is to just think of it as an infinite polynomial, right? Now, what does it mean for this object? What does this actually mean for me to write down an infinite polynomial? How does that even make sense for me to write down? For us, it's going to make sense in the same way that you would think a polynomial makes sense. So if you look at y equals x squared, how do you think about that? Well, one, yes, you can think about the graph. It's a parabola. Another way you can think of it is as a list of coordinates. I just know if I plug in x equals 1, the output is 1. If I plug in x equals 2, the output is 4. If I plug in x equals 3, the output is 9, etc. I can plug in a bunch of values and plug in a bunch of x values and compute a y value. In the same way, we're going to want to make sense of power series in that same way. Meaning, I have this infinite polynomial. If I were to plug in an x value here, what would the output be? Would that make sense? You'll notice that if I plug in an x value, it will just create a number here, a number here, a number here. In fact, all of these are numbers. Let me make sure to state that here. So when you're talking about a power series, it has this form. Let me make sure that you know where Cn is a constant. Cn's are constants. Given by a sequence. Your x is a real variable. So it's just a variable in which we can plug in a real number. And your x naught is just a particular real number. So some point on the number line you can think of it. So here, how can I make sense of this? Well, we can make sense of it by thinking of it sort of as a function, the same way we would think of as a polynomial. If I were to plug in an x value, what is the corresponding output? Notice that if I plug in an x value, now I just have a list of numbers, because this is a constant, that's a constant, that's a constant, all the c's are constants, the x naught is a constant. So once I plug in a value for x, that creates a constant. So I'll have adding a bunch of constants. That's just me adding up a bunch of numbers. That's what a series is. We know what that is. That's just a series. So for that thing to output a number, what has to happen is the series would have to converge for a particular x value. How do we know if the series would converge for a particular x value? So let's actually jump forward to talking about a power series. Now, we use the language of convergence, right? So when a series adds up to a meaningful value, we say it converges to that value. That was the language we use. So let's actually talk about when a power series converges to some meaningful value. First, before knowing how to test that it will converge to a meaningful value, let's actually talk about just the convergence of power series in general. That's something you would want to know about. So, the convergence of power series. So we know what a power series is. Let's talk about their convergence. It turns out that we can talk about convergence. We can know about this based on one particular theorem. So this is a theorem. So the power series Cn x minus x naught to the n 0 to infinity has specifically three possibilities for convergence. Okay. Here's one situation. The series converges only for x equals x naught. Right? So again, this guy is a guy that looks like C0 plus C1 x minus x naught plus C2 x minus x naught squared plus C3 x minus x naught cubed plus dot 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 dot. Okay? So here's one possibility, is that it converges for x equals x naught. Now I want you to notice that this is always actually going to be an option. If I plug in x equals x naught, what would happen is this guy would be 0, that guy would be 0, that guy would be 0. I'd get an infinite list of zeros. Now of course from this point onwards, that's all going to add up to 0. And so the entire series is just going to add up to C naught. Whatever the first coefficient is will be what the series adds up to. That will be your output. That would make sense, right? It will make mathematical sense. You'll just get a real number output, right? So one possibility is to plug in the x value that's going to kill an infinite number of terms and just leave one term remaining. This is always going to be a possibility for convergence. It will converge if I plug in x equals x naught specifically. There's another situation that can occur. The series converges for all real x. Sometimes it's possible, and we'll look at examples, where no matter what x value I plug in here, I will get an infinite sum, and that sum is actually going to add up to a number that makes sense. So it will work on the entire real line. Any x value I plug in, this series will add up to something meaningful. Here's a third situation, the last situation. The series diverges? No, it actually turns out the series will converge for all x such that x minus x naught. All x values that are within some distance from the center, we'll call it big R. Where big R is a positive real number called the radius of convergence. Of the series. So here's something I want you to appreciate about this theorem. One, this theorem tells you that a power series will never actually diverge. Let me just step out of the way here. So you can pause the video and copy this down, or just listen to me serenade you with some facts. This theorem tells us that a power series is never actually going to diverge. It will never diverge. There are only going to be three possibilities. One, the series will converge only for one particular x value, namely if I plug in x equals x naught. Another possibility is the series will converge for all real x. So no matter what x I plug in, it's going to work. Another possibility, it will only converge for x values for which such an inequality is true, where our R is going to be a positive real number called the radius of convergence. Now I will abbreviate radius of convergence as ROC moving forward because I don't want to have to write that down. First of all, I also want you to notice what this actually means. Note, just to flesh this out a little bit so that you understand what that means. X minus x naught less than R, what does that actually mean? Well, if you kind of interpret this the way that you would hopefully know how to interpret such an expression all the time, this means minus R is less than x minus x naught less than R. This means that x naught minus R less than x naught plus R, right? This means an inequality takes effect like this. We know it's going to converge for all x values in between the center minus a little bit and the center plus a little bit, right? So this opens an interval on the real line on which we would converge. So this guy here, by the way, this guy here is called the interval of convergence. Or IOC. And one thing about the interval of convergence, it may or may not include the endpoints, and we're going to talk about that as well. It may / may not include the endpoints. So R is called the radius of convergence. I would abbreviate it ROC. And sometimes a power series will converge for all x for which this inequality is true. I'm going to talk a little bit more about what that means in a little bit. But ultimately that means it will converge for all x falling in this interval where the endpoints may or may not work. And this interval is called the interval of convergence, or the IOC, as I would abbreviate it. Let's actually illustrate some things here, because this is a little bit abstract so far. Let's just kind of mention, let me kind of show you what each of these scenarios is talking about. So, illustrations. First situation. The first situation is saying you have a real line. This is the real number line. And the series only converges at one point. Namely, there's a point on the real line, x naught. This is where our series is centered. And the series only converges here. Okay. Now I want you to notice in this situation, so this basically means if I pick any other number on the number line and plug in that number into the series, it's going to diverge. It's not going to make any sense. But if I plug in this particular number, everything's going to be hunky-dory, the series is going to converge, and it will make sense. Namely, the series is actually going to converge to the value c sub 0. So in this case, your radius of convergence is 0, and your interval of convergence, well, it's not really an interval, it will just be the value x naught. So that's one possibility. Another possibility is here's the number line, here is x naught, but the series will actually work everywhere. So the series will work on the entire real line, meaning if I plug in this x value, it's going to work. That x value, I can plug in any x value anywhere along the real line. If I plug it into the power series, I will get an infinite sum that's going to converge to a real number, a meaningful answer, right? So one way to express this is to say that your radius of convergence is infinite, and your interval of convergence is, well, the entire real line, minus infinity to infinity. So I can plug in any x value in the power series, it's going to make sense when I add it up. Here's a third possibility. You can have the point x naught. Now, I'm not allowed to plug in any real value I want, but there's a distance I can move to the right and to the left of x naught. This distance, namely, is r, called the radius of convergence. And it can go up to x naught plus r, it can go down to x naught minus r. And as long as I'm within this window, the series will converge. So if I take any x value inside this window and plug into my power series, I would get an infinite sum of something that makes a real number answer. I can think of that as the output of the function. And if I plug in anything outside of this, then it's not going to make a meaningful answer. It's actually going to give me a divergent series. Here, your radius of convergence equals r, where it's just some real number. Your interval of convergence, well, it's going to be x naught minus r or x naught plus r. But the thing is, the endpoints may or may not be included. So you can think of it as, well, it's possible to include the left, but not the right. It's possible to include the right, but not the left. And it's possible to include both of them. Chalk dust making me sneeze. So your IOC would be one of these, or okay. So the endpoints may or may not be included, but this is all possibilities. So a power series is always going to converge. It will converge all the time. All power series converge. The question is, where is it going to converge? Is it going to converge for a single point only, x equals x naught? Will it converge on the entire real line? Or is it going to converge in some interval, centered here, where the radius of convergence is, like, you think of x naught as the center, and this is kind of where that language comes from, and you just take the maximum distance you can go away from the center. You can't even imagine a circle. Of course, in higher dimensions, we would get like a ball or a circle, but of course we're in calculus 2, so we're only doing single variables, so just a real line. So the radius is just the distance from the center to the outer edge. And we are in the case where if I plug in any value in here, my power series is going to make sense. If I plug in any value outside of that, it's not going to make sense. So hopefully that's clear. That's just something to illustrate. Hopefully it helps your intuition out You'll probably never have to actually draw one of these intervals. But that's just something that hopefully helps you. So now the question might be, how do we go about finding such a thing? How do we actually go about finding the radius and interval of convergence of a power series? So this is Calc 2 answer. Now in general there are going to be a multitude of answers, but we're in Calc 2, so we're really going to take the easy way out. Pretty much anytime I would ask you to find the radius of convergence or the interval of convergence of a power series, the answer is always going to be the same. Use the ratio test. Always the ratio test. Always the ratio test. Every time I ask you to find the radius of convergence or interval of convergence of some power series, you are going to apply the ratio test. One reason why you can see that the ratio test is really nice, remember the ratio test says we have convergence of a series if the limit of an plus 1 over an is less than 1. Now you'll notice that if I take the limit, plug in my power series terms here, I'm going to get some blah in here less than 1. Now that automatically tells me that the blah, it automatically gives me an interval on which that limit is going to work out. Now this is going to be some expression with x's in it. Hopefully from that expression, I can actually find the radius and interval of convergence. So the ratio test is very nice in the sense that it will actually, just by applying it, we automatically will get some sort of interval where we know that things will work or not work. The root test also has a very similar idea. However, it's not very typical in a Calculus 2 class to actually use the root test to figure some of these out. Maybe you might get a problem like that on your homework, but anything that I would ask you in class, it's the ratio test. Always the ratio test. Yeah, that's it. Now, me just saying, hey, use the ratio test, probably is not going to tell you how to actually do it. So let's actually just do some examples so you can see specifically how would you use the ratio test to actually determine these two things. But that's how you determine them. So let's look at some examples. And the ROC and IOC of the following. Here's the first example. The series n goes from 0 to infinity of x to the n. B. The series n goes from 1 to infinity of x minus 4 to the n over 2n. C. The series n goes from 0 to infinity of x to the n over n factorial. Pause the video, copy those examples down. We are going to go through those three examples and we'll see how much time we have after going through those three examples and me explaining the nuances of those three examples. Yeah, so we have these examples. Now, the first thing, before I actually move on to doing these examples, I do want you to appreciate the fact that these things that I just wrote down, they're not just regular series, they are in fact power series. So, how would you see that these guys are power series? Notice that this guy here, it's like me saying n goes from 0 to infinity of 1 times x minus 0 to the n. So this is a power series where your Cn is always given by the function 1, and your x naught is actually 0. You might notice here, this I can think of as a power series. This is n goes from 1 to infinity of 1 over 2n times x minus 4 to the n. So this is a power series where your Cn is equal to, let's say, 0 if n equals 0, but it's equal to 1 over 2n otherwise. And your x naught is 4, right? So that's x minus x naught to the n. And what's in front of that is my Cn. Now this guy here, I can think of this, n goes from 0 to infinity, of 1 over n factorial times x minus 0 to the n. And that's another one, that's a power series where my Cn is 1 over n factorial, and my x naught is again 0. Right? So these guys are all power series. This one's centered at 0, that one is centered at 4, this one is also centered at 0. This one has a coefficient given by the function Cn equals 1. This has a coefficient given by Cn equals 1 over 2n, except when n equals 0, because this guy starts at 1. When n equals 0, I can just set the Cn to be 0. And this one has Cn equals 1 over n factorial, and it's centered at 0. So these are all, these objects that I just wrote down on the board, these are all power series. So this actually they actually fit in with the definition that I had in the beginning. So now that I know these are power series, how do I go about finding the radius of convergence or the interval of convergence? What are the numbers that I can plug into this guy and get something meaningful, get a meaningful output that I can create a list of coordinates with to create a function or something like that? So let's actually start from the beginning. Now the first one I'm just going to run through so that you can see the idea, but for the next two, for B and C, what I would like you to do is, before I do them, pause the video. You know the drill, we've been doing this before. Pause the video and actually try them and let me know. So this guy, if you actually looked at what this looks like, it's 1 plus x squared plus x cubed plus x to the 4th plus ... So it's an infinite polynomial where the powers of x are from 0, 1, 2, 3, going on forever, and the coefficient is always 1. Now, this is not me doing the problem, but just to get a little bit of intuition going here. Notice that if I were to plug in x equals 0, what would this actually mean for the sum? I would get a series that looks like 1 plus 0 plus 0 plus 0 plus blah, blah, blah. Notice that this will converge. It actually converges to 1 in this case, right? So if I plug in x equals 0 into this series, it will actually make sense. It will actually add up to 1. And so it would converge in that situation. What if I plugged in, say, x equals 1? Go here into this infinite polynomial. Everywhere I see x, I put 1 instead. What would I get? I would get 1 plus 1 plus 1 plus 1. Now that should automatically tell you that that diverges. You can do the test for divergence to know that that would diverge, but a series where you're always getting 1, the limit is not going to hit 0. Test for divergence tells you that diverges. But this also just tells you that 1 plus 1 plus 1 is going to add up to something big. It just keeps getting bigger. So it would actually diverge at 1. What if I picked another value, say x equals a half, right? Halfway between 0 and 1. I would get, if I plug in x equals a half, 1 plus a half, plus a quarter, plus an eighth, plus a 16, plus so on and so forth. Now, this example should be familiar to you. If I forget about the half, you might remember that this was the example that I mentioned when we started introducing series, and I spoke about the dichotomy paradox and what it would take to actually walk a mile. You'd have to first walk a half a mile, then a quarter of a mile, then an eighth of a mile, and we just knew, oh, this sum was the way of dissecting 1 mile. So we know that that adds up to 1. all of this. And then I put a plus 1 again, so this actually adds up to 2. This guy actually converges. Converges to 2. And we actually showed that in a couple ways. There are 2 ways in which we derived that actually converges. So yeah, notice here, this is an infinite polynomial, but it does not work everywhere. I plug in 0 and a half, it works, I can get a coordinate, right? So this will actually pass through a half comma 2. It will also pass through 0 comma 1, whatever this, if I want to think of it as a function. However, there is no x equals 1 for this function. It doesn't actually make any sense that x equals 1. So the question is, what are the x values for which it makes sense? What are the x values for which it does not? Let's actually talk about that right now. So what we're going to do is we're going to find the radius of convergence and the interval of convergence. This is going to tell me what x values am I allowed to plug in, and it's going to actually make sense when I plug in those x values. Okay, that's the goal. How are we going to do it? Ratio test. Always the ratio test. When it comes to this particular thing. Okay, so employ the ratio test. Now, that's just a phrase that is very typical to use. I don't want to. I know a lot of people are probably struggling with employment right now, but I don't know. That's just a phrase that we use. Hopefully, all of you are okay, and hopefully everyone's going to be okay. It's going to really suck for a while, but we will bounce back. Don't worry. The ratio test, in the meantime, is an essential employee. It will always have a job as far as math is concerned. So we're going to employ the ratio test here. This is going to be, the ratio test means we're going to set L equals the limit. Of course, it's always the limit as n approaches infinity of the series when I plug in n plus 1 divided by the series term when I plug in n. Now, of course, this would simplify and I would have that. Now remember, this is the limit as n is approaching infinity. So what does that limit approach? Pause the video, tell me the answer. 3, 2, 1. Okay, what's the answer? Well, hopefully you said that the answer was absolute value of x, because that would be correct. Now what you would do is, you know what the ratio test says. If this limit is less than 1, we have convergence. So for convergence, in fact for absolute convergence, but let's just talk about convergence right now, absolute value of x must be less than 1. Now this automatically tells you one thing. First of all, it tells you that the radius of convergence is 1. You can know that right off the bat. Why? Because this is x minus 0 is less than 1. So that kind of looks like your x minus x naught less than r, where that's just your x, your 0 is the x naught, and your 1 is the r. Right? So that's one way you can tell. There's another way that you can talk about the radius of convergence that I will show you later on. Pretty much another way to find the radius of convergence, which is a little bit more easier to grasp intuitively by students, is to find the interval of convergence and then just take half the length of that interval, right? Just think of the center and then what is half the distance? That is the radius of convergence, right? So you can actually tell right here, but we can actually wait until later as well. So we can know that the radius of convergence is 1. Now, this gives us, for the interval of convergence, if your x is less than 1 in absolute value, this of course means that minus 1, x is between minus 1 and 1. But now you don't know whether the endpoints are going to work. So we are going to continue. We're going to check the endpoints. So if x equals minus 1, what's going to happen? What I'm going to do is I'm going to plug in -1 into this series. I would get the series -1 to the n. Now, does this actually converge? Pause and answer. It does not converge. So we know that this diverges. How do you know that diverges? That's right, test for divergence. Okay? So the limit as n approaches infinity of -1 to the n is not 0, therefore it diverges. If I plug in x equals 1, so I'm going to go here, plug in x equals 1, I'm going to get 1 to the n, I would get the series, n goes from 0 to infinity of 1. And again, that diverges. By test for divergence. And this will tell us that the interval of convergence is just the interval between -1 and 1, not including either one. And your radius of convergence is 1. Now again, I can know that the radius of convergence is 1 because if you look at the number line, it's centered at 0, goes down to -1, goes up to +1. Half that distance is going to be 1. If you don't know if that half the distance is 1, you could actually do b minus a over 2, right? And so 1 minus a -1 over 2, you get 1 in that way. So radius of convergence is just half the length of the interval of convergence. So you can actually just fully do the problem, find the interval of convergence, half the length of that interval is the radius of convergence, or you could have found the radius of convergence earlier as I mentioned. Yeah, so that's the first one. Copy that down. I'll give you 3 seconds to pause. 3, 2, 1, pause. All right, now we're going to do the second one. Now, for the second one, I would like you to pause. Actually, pause the video, try it on your own. Whether or not you get stuck does not matter. Try your best. Get through the whole problem, use what I just did as an example, and approach it that way. So you're going to apply the ratio test, you're going to find the interval, you're going to test the endpoints, then you're going to conclude whether or not it includes the endpoints or not, then you're going to write down the interval of convergence and the radius of convergence. So take a few seconds to actually pause. So I'll give you 3, 2, 1. Pause, try the problem. Now hopefully you try the problem. I already spoke about this. It's actually very, very important. It's more important than ever that you're not in class to ask me questions. I mean, you still can ask questions like in the comment section or email me through Jupyter Grades as I mentioned, but to get the most out of this distance learning thing, a lot of you really need to make up. You're not doing so hot after test 1, and like I mentioned before, I'm pretty sure I mentioned that before, it's still anybody's game. As far as I'm concerned, anyone can still get an A, but if you're not doing so well so far, it might not be easy to get an A. One way that you're going to want to make sure that you have the best chance possible is whenever I tell you to pause the video and try the problem, you pause the video and try the problem. You need to try, right? You can't just watch me do everything. It's not going to work out for you. It's not going to help. You actually try to engage as much as possible. So try that. And let's go. Now I'm going to jump in and start this, but I'm trusting you to pause the video and actually try to do this problem. So just for fun, just writing out what this would actually look like. If you wrote n equals 0, you would have x minus n equals 1, sorry, you'd have x minus 4 over 2 plus x minus 4 squared over 4 plus x minus 4 cubed over 6 plus x minus 4 to the 4th over 8 plus dot dot dot. So this guy actually looks like this polynomial. Now, in the same way, I'm going to want to know what x's am I allowed to plug in here and actually get a meaningful answer. Can I plug in any x value? And is that going to work? Could I plug in x equals 0? Would that make sense? Right, if I plug in x equals 0. What if I plugged in x equals 10? What if I plugged in x equals 17? We want to know these things. How do we know what x values for which this is going to work? So, how do we know? How do we find out? Ratio test. Always the ratio test. So, by the ratio test, we're going to set up the limit as n approaches infinity. Like, we don't write it down, but we know that's what it is. X minus 4 to the n plus 1 over 2 times n plus 1. Now, instead of dividing by that, I'm going to flip and multiply by the reciprocal. So that's what that looks like. I can actually simplify this a little bit. 2 would cancel the 2. This guy is going to cancel that. And let's rewrite. So this is the limit. And this will give me n divided by n plus 1, by moving this n from here, times, I'd be left with x minus 4. Now, hopefully you got up to this far. If not, maybe you can redeem yourself by telling me the next step. What is this limit actually going to be equal to? Three, 2, 1. Well, hopefully you got that it's equal to x minus 4 in absolute values. Because we know that this guy here is going to approach 1. And so we're left over with the x minus 4 in absolute values as n approaches infinity. Now, I'm going to set this less than 1 for convergence. Now, this tells me two things. First of all, this tells me that the radius of convergence is 1. Again, because this looks like x minus x naught, which it's centered at 4. And I get less than r, and my r in this case is 1. So I know that's the radius of convergence. We'll be able to find it later as well. So if that confuses you, which understandably a lot of students are confused by this part when you pick out the radius of convergence this early. If I remember, even I was confused about that part a little bit for a while when I was learning this for the first time. So if you didn't pick out the radius of convergence here, if you can see that that's the case, great. You'll have another chance to actually pick out the radius of convergence later. So let's move on. Another thing that we know is that if our x minus 4 is less than 1, then that means minus 1 is less than x minus 4 is less than 1. And that means that our x is between 3 and 5. So what we're going to do now is we're going to test the endpoints. What happens at x equals 3 and 5? I know it's going to work for everything in between 3 and 5. In fact, it's going to converge absolutely in between 3 and 5. What is going to actually work out for test the endpoints? Check endpoints. X equals 3. If I plug in x equals 3 here, I would get minus 1 inside of that. So that's minus 1 to the n over 2 to the n. Now, if you got this far, congratulations. If you didn't get this far, try to redeem yourself by telling me the next step here. Does that converge? And the answer is yes. Hopefully you got that. So this is 1/2 minus 1 to the n over n. This is the alternating harmonic. We actually showed that converges before, and then we're just multiplying by half. So this converges by the alternating series test. By the way, by the time you get to this point, I would expect you to be able to glance at a series and know that it's going to converge. You don't have to fully justify it for something like this, but you just tell me, how do you know that the thing converges or diverges? If you plug in x equals 5, we would end up with the series n goes from 1 to infinity of, we'll actually end up with 1 over 2 to the n. Now, converges or diverges, this guy. Diverges, that's right, it is harmonic. This is 1/2 times the series of 1 over n. You could say diverges, since harmonic. So we have a situation here, this particular power series, its interval of convergence is all numbers between 3 and 5. It includes the 3, but not the 5. So this means the interval of convergence is 3, all numbers between 3 and 5, inclusive of 3, but not of 5. So that's your interval of convergence. Now, of course, your radius of convergence, you can think of just half the length of that interval, b minus a over 2, 5 minus 3 over 2, it's 1. Right? So your ROC is 1. So here, for this series, it is centered at 4. It goes all the way down to 3, and it works at 3. But it goes up to 5, it does not work at 5. So the radius of convergence for this power series is 1. The interval of convergence is 3 to 5, inclusive of 3, not of 5. And basically what that means is if I have to plug in any x value in between 3 and 5, not including 5, then this series is going to add up, the infinite sum will converge to a meaningful value. If I plug in anything outside, like if I plug in x equals 0, it's not going to work. If I plug in x equals 1, it's not going to work. Plug in x equals 6, it's not going to work. Plug in x equals 10, it's not going to work. It will only work for x values between 3 and 5, not including 5. Now hopefully that gave you, if you didn't get through this example, hopefully that gave you a little bit more practice on how you want to approach this. So you're going to pause the video, you're going to try the third example that I'm going to mention here, and then you are going to try this, and then start the video again. Right? So this series, if you want to write it out some, when n equals 0, you have 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. You can also write that out as 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120 plus that. Right? So it's just an infinite polynomial that looks like that. Right? Now, the question is, what x values am I allowed to plug in? It should be obvious that plugging in 0 is going to work. It's going to converge to 1. What about plugging in a half? Plugging in 2, plugging in 7, plugging in 10? What am I allowed to plug in here and get a meaningful answer? When is this thing going to behave somewhat like a polynomial? Just a nice function that I can plug something in and get something out. Well, let's go. What you should do now is pause the video, try the problem. Give you 3 seconds to pause. 3, 2, 1. Okay. Let's actually do this. So what we're going to do here is employ the ratio test. We would look at the limit of x to the n plus 1 over n plus 1 factorial times the reciprocal. That's going to cancel into that. Ln factorial cancels the factorial part of that. This is going to leave us with the limit of x over n plus 1. Now, hopefully you got up to that far. And now what's the next step? What is actually that limit? Remember, it's the limit as n approaches infinity, which means the limit does not care about the x. Okay, that's right. Limit is 0. Now, what does that tell you about the convergence of this power series? Well, something that's special about 0, it's less than 1, always. Notice that we ended up with the limit being just a constant that's less than 1, meaning my particular x value doesn't actually matter. 0 is always going to be less than 1, which means no matter what x value I plugged in here, eventually the denominator is going to overwhelm that number, and it's going to go off to 0, which is it's going to always give me a number less than 1. What does that tell you about convergence? What is the radius of convergence? What is the interval of convergence? Well, this means convergence for all x. All real x. So that means your radius of convergence is infinite, and your interval of convergence is the entire real line. The interval from minus infinity to infinity. So that's that guy. Now, hopefully you got that as the answer. Hopefully you got the last part as the answer. If not, anything still confuses you, drop questions down in the comment section or email me through Jupyter Grades. That being said, that is this problem. Now, this series is actually an important series, actually a known series. I don't know if any of you would know what that is, but if you do, good for you, brownie points. If not, don't worry, we'll actually be seeing that guy in a couple lectures, and we'll actually talk about what that guy actually is. Now, I did mention briefly to my Calculus 1 class what that series actually adds up to, yeah, that was a long time ago. It was literally like a 5-second thing in my Calc 1 class, and then we moved on. One thing I do want you to do, though, and probably you guys can comment on this and let me know. Question to start off the next lecture with, as well as I'll start off the next lecture with Q&A. I didn't get any Q&A for this lecture, though, so apparently, hopefully everyone understood the last lecture. I'm going to go with that assumption, because what else can you do, right? So here's a question for the next class. So I'm going back to the first example we had here, the series x to the n, and it goes 0. Now we know that that converges for x values between minus 1 and 1, strictly speaking. But as long as my x values are within that range, what does this converge to? So think about that question for next time. Actually try to think about that question. Don't just wait for me to tell you the answer in the next class. It's important to know. And if you don't know how to come up with that question, go back, review all the series convergence tests. You should see something that hints to you that question. And looking back at those, you should have some idea. I know it's been a while, it's been an entire spring break, and a lot of craziness is going on. So you're probably just not up to speed on what happened before this whole thing started happening. So take some time. It is definitely necessary. It is definitely worth it. Take some time. Go back over the stuff that you've forgotten that I was mentioning, especially about series, and make sure you try to answer that question by the next lecture. And if you don't know the answer to the question, then I don't know. We'll have to deal with that moving forward. But that's it. That's it for the lecture. Like I said, I hope you enjoy your spring break, or however much you could do that. I know it's a really it's a difficult time for everybody, myself included, but I know there are a lot of people out there who have things a lot worse than I do. So hoping you guys are safe, hoping you guys are healthy, and hopefully you guys are actually still putting in the work, because the world is not going to stop turning. This is just a little hiccup which we will recover from. Once we recover from it, are you going to be good at Calc 2? Because you better be good at Calc 2 when we recover. That's going to be important for the future. So answer that question for next time. Drop any questions about this lecture down in the comments section, or email me through Jupiter Grades. I will see you guys in the next one. Peace.